Hello everyone. Today we'll be going over Chapter 5, otherwise known as Discrete Probability Distribution / Binomial Distribution. This chapter is broken down into two parts. The first part is called Discrete Probability Distributions, which we will see in Problem 1, and the second part is called Binomial Distributions, which we will see in Problem 2, 3, and 4. Discrete Probability Distributions. We'll begin by looking at the definition of a random variable. A random variable is a variable whose value is numerical and is determined by the outcome of an experiment. A random variable assigns one and only one numerical value to each experimental outcome. It's important to understand that there are two types of variables. The first one is discrete and the second one is continuous. In this chapter, which is Chapter 5, we'll be dealing with discrete random variables, and then in the next chapter, Chapter 6, we'll be dealing with continuous random variables. The key difference being that discrete has a limited, fixed number of outcomes, while continuous random variables tend to have many outcomes that are difficult to count. When dealing with a discrete random variable, which we will do in this chapter, we will deal with two formulas. The first one is our mean formula, which is right here. And it states that the average for a discrete random variable can be found by taking each variable or each possible outcome, x, multiplied by its probability and adding them up all together. The next formula we have is the variance formula, which can be found by adding up the difference between the x value and the average, squaring that answer and multiplying it by the probability of that outcome and adding up all those values together. Binomial distributions. For a distribution to be considered binomial, it must follow the following four rules. 1. The experiment must consist of n identical trials. 2. Each trial can only have two possible outcomes. 3. The probability of success p is constant from one trial to another. And 4, the trials are independent. Once these four rules have been checked off, we know we're dealing with a binomial distribution, and we can move on to using the binomial formulas. The formula for mean, which is denoted here, is simply n, meaning the number of outcomes multiplied by the probability. The variance is n, again meaning the number of outcomes multiplied by the probability of success, which is denoted as p, multiplied by the probability of failure, which is denoted as q. And lastly, we have a formula to find the probability of any given outcome. For example, the probability of getting 3 out of 5 or 6 out of 15. We use the following formula, and the formula is broken down into three parts. The first part is the basic combination formula, where n represents the number of outcomes and x represents the number of outcomes you were looking for. The second part, which is p to the power of x, is the probability of success to the power of the number of successes you're looking for. And the last part is 1 minus the probability of success, or the probability of failure, to the power of n minus x, which would give you the number of outcomes minus the number of outcomes you're looking for. Problem 1. A bank vault holds large numbers of banknotes of different denominations. On a typical day, 5% of the banknotes are $2 bills, 15% are $5 bills, 25% are $10 bills, 35% are 20s, 10% are 50s, and 10% are $100 bills. What is the variance in all the values of the bills held in the vault? Before we begin, let's highlight the important information the problem gives us. It tells us that 5% are $2 bills, 15% are $5 bills, 25% are $10 bills, 35% are $20 bills, 10% are $50 bills, 10% are $100 bills. Now, to find the variance, we must use the variance formula, which is at the top right corner. However, in the formula, it requires the mean, which we don't know, so we're going to have to find the mean first, and the formula for the mean is directly above the variance formula. the mean formula states that the mean is equivalent to the sum of each individual x value multiplied by its probability. So we're going to begin with the $2 bill. $2 being the x value multiplied by its probability of 5% plus the next x value, which would be $5, multiplied by its probability of 0.15 plus the next x value, which would be $10, multiplied by its probability, plus the next x value, which would be 20, multiplied by its probability of 0.35, plus 50, multiplied by its probability of 0.10, plus 100, multiplied by its probability of 0.10 as well. And this would give you an answer of 25.35. And this number is the mean. Now we can move on to finding the variance. The formula for variance is as follows. X minus the mean squared multiplied by the probability of each individual x. However, I recommend doing a slight adjustment and rewriting the formula as the sum of the probability of x multiplied by x minus the mean squared. The reason you want to make that slight adjustment is in case you're trying to do it all in your calculator. By putting the probability at the end, your calculator might give you an error, but by putting it at the beginning, it'll work and it won't give you an error. So we're going to begin. We're going to begin with $2. The probability for which was 5%, so 0.05 multiplied by 2 minus the mean squared plus 5 minus the mean plus 0.25 minus the mean squared plus 0.35 for the probability, 20 for the x value, minus the mean of 25.35 squared plus 0.10 for the probability, multiplied by 50 for the x value, minus the mean of 25.35 squared plus 10 multiplied by 100 minus the mean squared to give us a final answer of 776.33, which is our variance. Problem 2. A doctor estimates that 5% of her patients have no real physical ailment. A random sample is taken of her records and it is found that 3 out of the 15 sampled patients had no physical ailment. What is the probability of observing exactly 3 patients who have no physical ailment in a sample of 15 if the population proportion is actually 0.05? Well, before we begin, let's highlight the important information the problem gives us. It tells us that 3 out of 15 people sampled, or patients sampled, had no physical ailment, and that the proportion with no physical ailment should be 0.05 or 5%. What they're asking us to do is to find the probability of observing 3 out of 15 people who have no physical ailment if the probability of someone with no physical ailment is equal to 5%. For this problem, all we have to do is understand the binomial formula, and we're going to begin by labeling all our variables. Our n, which is the total number of observations, in this case would be 15, since we observed 15 patients. Our x would be the ones without a physical ailment, which in this case they tell us it to be 3. Our p, which is the probability of someone not having a physical ailment, is 0.05 or 5%, and our 1 minus p, which is the probability of p not occurring, and is sometimes noted as q, would simply be equal to 1 minus p, which would give us 0.95. Now that we have all our variables, we can plug them into our equation. And we will get an answer of 0.0307, meaning that if there is a 5% chance of a patient having no physical ailment, there is a 0.0307 or 3.07% chance of 3 out of 15 people having no physical ailment. B. What is the probability of observing 3 or more patients who have no ailment? This question is very similar to A, but the key difference being that in A, they were asking us for the probability of exactly 3 patients having no ailment, while in B, they're asking us for the probability of observing 3 or more patients who have no ailment. B would be the probability of X being greater than or equal to 3. Now, since our sample size is 15, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. There's a chance of 0 out of 15 having no ailment, 1 out of 15 having no ailment, 2 out of 15 having no ailment, all the way to 15 out of 15 having no ailment. And the question's asking us for 3 or more having no ailment, which would give us the probability of X being greater than or equal to 3, which is what we're looking for. However, the binomial formula only allows us to input one X at a time. So inputting all those X's would take quite a bit of time. However, there is a shortcut. Since we know that all probability must add up to 1, we could find the probability of what we're not looking for, which would be the probability of X being less than 3. Once we find that answer, we would take 1 subtracted by the probability of X being less than 3, which would give us the probability of X being greater than or equal to 3. And using this method, we would only have to test 3 X's, 0, 1, and 2. Since this method is shorter and it will give us the same answer, that's the method we're going to use. We're going to plug in each X individually, our X's being equal to 0, 1, and 2, into our binomial formula. Our N in the formula will be 15 as before. Our X will change from 0, 1 to 2. Our P will be 0.05, same as before, and our Q will be 0.95. We will begin by testing 0. Which gives us an answer of 0.4633. We would then test 1. which gives us an answer of 0.3658. And we will test 2. Which gives us an answer of 0.1348. We're going to add up our values. Which gives us a total of 0.9639, which is the probability of x being less than 3. However, we're looking for the probability of x being greater than or equal to 3. So we will take 1, subtracted by our answer. Which should give us an answer of 0.0361. Which is what the answer we're looking for. And it is the probability of x being greater than or equal to 3. This is our final answer. For B. Problem 3. Several airlines run a commuter service between Washington, D.C. and New York City. Because of traffic congestion at the airports of both cities, commuter flights are often delayed by as much as 2 hours. Recent evidence shows that 25% of the Washington, New York commuter flights run more than 30 minutes late. Suppose 4 commuters each take a different Washington-New York flight on 4 different days. Assume the flights to be independent of each other. A. Find the probability that all 4 arrive in New York within 30 minutes of their expected arrival time. And B. Find the probability that at most one commuter is more than 30 minutes late arriving in New York. Before we begin the problem, we're going to highlight the important information the problem gives us. It tells us that 25% of the Washington-New York flights run more than 30 minutes late, and that we're testing 4 commuters. For this question, we will need a binomial equation, which is the formula for which is right here. And we'll begin by labeling our n, x, p, and q. Our n in this case would be 4, since we have 4 commuters. Our x, the problem tells us that there is a 25% chance of a flight running late. However, is A asking us for the flight running late or arriving on time? It is asking us that the 4 flights will arrive within 30 minutes. Therefore, they're asking us for them to arrive on time, while the 25% is for them to arrive late. Therefore, the 25% is not our P, but rather our Q, since it is the probability of the commuters not arriving on time. And if our Q is equal to 0.25, our X is the difference, which is 0.75, since we know that our P plus our Q must be equal to 1. And problem 8 tells us that we want all 4 to arrive on time. Now that we have all our variables, we can simply plug it into the equation and get our answer. And that gives us an answer of 0.3164, which on the exam you could write as a sentence, or leave it as a decimal, or even put it as a percentage, which represents the probability of 4 out of 4 commuters arriving within 30 minutes of their expected time. Let us move on to B. Find the probability that at most one commuter is more than 30 minutes late arriving in New York City. So now, the chances of at least one commuter arriving late can be translated to at least 3 being on time. The reason we want to make that translation is since we already set up our problem for A in terms of being on time. So instead of retranslating it to being late, we're just going to translate the question B into being on time. The question's asking us that one commuter will be more than 30 minutes late, which is equivalent to saying that either 3 out of the 4 will be on time, or 4 out of 4. Will be on time. So now, since we already have the answer for 4 out of 4 from above, we're just going to recopy it. And we're going to look for the probability of 3 out of 4 being on time. We're going to plug it in to the equation using 3 as an x this time, but keeping all the values the same. And that'll give us an answer of 0.4219. We will add up both values. To give us a final answer of 0.7383, or 73.83%, which is the probability of at most one commuter being more than 30 minutes late, or at least 3 out of 4 commuters being on time. Problem 4. The transit system in Euralia has first, second, and third class seats, all with regular fares and reduced fares. Reduced fares are for seniors and children and are 50% of the regular fare price. 90% of the riders in first class pay the regular fare, and the others pay the reduced fare. 70% of the riders in second class pay regular fare of $2, and the other riders pay the reduced fare. 80% of the riders in third class pay the regular fare of 50 cents. 20% and 30% of the riders are in first class and second class respectively. So before we begin this problem, we're going to highlight the important information the problem gives us. It tells us there's 3 class seats and 2 fares, regular and reduced. It tells us that the reduced fare is 50% of the regular fare. 90% of all riders in first class pay $4. 70% in second class pay $2. 80% of the riders in third class pay 50 cents. And 20% and 30% of the riders are in first and second class, respectively. So now we can start translating this information to our table. I'd recommend building a table for this problem to keep things organized and simple. We will name our rows and columns. Our rows will be the fare price, being regular and reduced, while our columns will be the classes: first class, second class, and third class, with the last column being total and our last row also being total. The last statement tells us that 20% of all riders are in first class and 30% of all riders are in second class. Therefore, if we know the total must be equal to 1 minus the first class percentage minus the second class percentage should give us the third class percentage. The problem also tells us that the regular fare is 50% more than the reduced fare. And it gives us the price for all the regular fares. It tells us that regular fare first class is $4, regular fare second class is $2, and regular fare third class is 50 cents. Now, if the reduced fare is 50% less, we just divide each value by 2 to get the reduced fare prices. The problem then starts to break down the order between reduced and regular price. Here, it tells us that 90% of the first class riders pay regular fare. Therefore, if we know 20% are first class, and out of that 20%, 90% pay the full fare, that would mean that 18% of all riders are in first class and pay regular fare. By extension, if there are 20% of all the riders in first class and 18% of all the riders in first class pay regular fare, 0.02 must pay reduced fare. Applying the same logic to second class, which tells us that 70% of all riders are in 70% of all riders in second class pay regular fare. We know that 30% of all riders are in second class, times out of that 30%, 70% pay regular fare, which gives us 0.21, which represents the number of people who are in second class and pay regular fare. And if 30% are in second class and 0.21% are in second class and pay reduced fare, 0.09 must pay the reduced fare. And applying the logic once more to the third class, if we know that 50% are in third class and 80% of them pay regular fare, that would mean 40% of all riders are in third class and pay regular fare. And since 50% are in third class, and out of that 50%, 40% are paying regular fare, that must mean 10% of all the people on the train must be third class riders and paying reduced fare. Now that we have all our values, we'll simply add them up to make sure they make sense. Our bottom row does add up to 1, therefore it does make sense. Now we will add up our columns. This column will give us 0.21. This column will put 79, which does in fact also add up to 1. Therefore, the math is correct. I have recopied the answers from our table, and we will now begin with the problems. A. What proportion of riders pays regular fare? Since we've already completed the table, all we have to do is recopy the regular total answer of 0.79 or 79%, meaning that 79% of all riders pay regular fare. B. If a rider is selected at random and found to have paid regular fare, what is the probability that the rider paid a first class fare? This question could be reworded as, given that a rider paid regular fare, what is the probability that they are in first class? This question is a conditional probability question. Therefore, we will need the conditional probability equation, which is at the right below our chart. I'll rewrite it. It is the probability of A given B is equal to the probability of A intersection B divided by the probability of B alone. A being the probability of being in first class, and B being the probability of having paid regular fare. The formula requires us to simply translate B, which we know to be 0.79. However, we also need the intersection of both A and B, which is the people who paid first class and paid regular fare, which is right here, 0.18. And that'll give us an answer of 0.227 or 22.7%, meaning that given that person paid regular fare, there is a 22.7% chance that he or she is in first class. Now C, what is the mean amount of money paid per rider? What is the mean amount of money paid per regular fare rider? This question is broken down into two questions. The first one is asking us for the mean for all riders, while the second part is asking us for the mean for the regular fare rider. We will need the mean formula, which is right here. It is simply the value or the outcome x multiplied by its probability and added up all together. We'll begin by finding the total mean for all riders. And all we must do is take the price for the seat multiplied by the probability, $4 multiplied by 0.18 plus $2 multiplied by 0.21 plus 50 cents multiplied by 0.4 plus $2 multiplied by 0.2 plus 1 multiplied 0.09 plus 25 cents multiplied by 0.1 to give us a mean answer of 1.495. And now we can move on to the second part, which is asking us for the mean for the regular fare riders, which would be almost exactly the same, except we're only going to use the regular fares, which would be 4 multiplied by 0.18 plus 2 multiplied by 0.21 plus 50 cents multiplied by 0.4. The key difference here is this time we'd have to divide by the total of 0.79, which would give us an answer of 1.696. The reason why we divide by 0.79 is because in a mean formula, we always divide by the total, which in this case is 0.79. And in the previous case, the reason we did not divide was because the total in probability is always 1. And dividing by 1 would make no difference. D. A transit authority spot check is made by selecting 8 riders at random. What is the probability that at least 2 of them are reduced fare riders? What is the expected number of reduced fare riders amongst the 8? What is the standard deviation? We will begin by focusing on the first part of the question. What is the probability that at least 2 of them are reduced fare riders? This is asking us for the probability that x is greater than or equal to 2. And since we have 8 riders, we have 9 possible outcomes, meaning that there's a chance that 0 out of 8 are reduced fare, 1 out of 8 are reduced fare, 2 out of 8 are reduced fare, all the way to 8 out of 8 being reduced fare riders. And it's asking us for the probability of 2 or more being reduced fare riders. However, since the binomial equation, which is right here, requires us to put in one x value at a time. It would take quite some time to punch in each one individually and add up their total. Therefore, we will use a shortcut. The shortcut is based on the complement rule, and since we know that the probability must always be equal to 1, we could find the probability for what we're not looking for, which would be the probability of x being less than 2, taking 1, subtracting it by that probability, and that would give us what we are looking for, the probability of x being greater than or equal to 2. We will begin by labeling our variables for the equation. Our n would be 8, since that's the number of riders we're testing. Our x would first be 0 and then 1. Our p would be the probability of a rider being reduced fair, which we would find on our table, which is 0.21. And our q, which would be the probability of a rider not being reduced fair, or in this case being a regular fair rider, which is also on our table and is equal to 0.79. We'll begin by using 0 and plugging our variables into our equation. 8 factorial over 0 factorial multiplied by 8 minus 0 factorial multiplied by 0.21 to the power of 0 multiplied by 0.79 to the power of 8, which would give us an answer of 0.1517. And we would do the same thing, this time using 1 instead of 0. Which would give us an answer of 0.3226. And now to find what we're looking for, we would simply take 1 subtracted by our answers, to give us 0.5257, which is what we're looking for, since it is the probability of x being greater than or equal to 2. And this is our final answer for that part of the question. This part would be the probability of x being less than 2. Now that we finish the first part, we can move on to the next part of the question. What is the expected number of reduced fare riders amongst the 8? To find the expected number of reduced fare riders, all we have to do, we'll call that part P1. This will be our P2. All we have to do to find P2 is take our 8 riders and multiply it by the probability that any rider will be reduced fare, which is right here. It is 0.21, to give us an answer of 1.68, which means out of 8 riders, we would expect 1.68 riders to be reduced fare. And now we will move on to the last part of this question, P3, for part 3, and they're asking us for the standard deviation. The standard deviation equation for a binomial distribution is very simple. It is the square root of n multiplied by p multiplied by q, which equals to the square root of 8, since that's the number of riders we're testing, multiplied by p, which is 0.21, the probability of a rider being reduced fare, multiplied by 0.79, which is the probability of a rider not being reduced fare, and that gives us a standard deviation equivalent to 1.15. E. If there are 75,000 riders on a randomly selected day, what is an estimate for the total amount paid in fares on that day? For this question, the first part, we would have to find the average each rider pays. However, we already found that number in part C, and it was equivalent to $1.495. Since this is the average each rider pays, pays, all we have to do is multiply the 75,000 passengers times the amount that each passenger pays to give us an answer of $112,125, which means that if there are 75,000 riders on a selected day, there should be about $112,125 paid in fares on that day. That is all for this video. Thank you very much, and I hope to see you guys next time.